Good afternoon. Good afternoon, ma'am. Right, ma'am. Okay, once again. Very good. Right. How can you able to see my screen, ma'am? Yes, ma'am. Not enlarged. Okay. Okay. emerging things in photovoltaic and optoelectronic application. The screen energy and is it the same as green energy and renewable? What is the differentiation you want to know? A clean energy refer to energy source. So if you refer this one, the energy source do not emit greenhouse gases or other pollutants, so that we call as a clean energy during the production. So most of this is natural sources. Clean energy refer to energy source that do not emit greenhouse gases or other pollutants during the production. Clean energy can include both, so we can classify it into both like renewable as ah, okay. Where it is on? Oh, still we are in online, huh? Okay, right.
ஆமாம்மா. சமயம் நம்ம வெளியே 2 தட்டு வச்சுருவாங்க. அது குடுத்துட்டு ஒரு 2 வருஷம் 30,000
Good afternoon to everyone. First of all, I like to thanks for inviting me for this 5 days faculty development program in Ethiraj College for Women. And I convey my thanks to Dr. S. Abhirami for organizing these things. And second, organizing secretary also like to thank Dr. Rajeshwari ma'am and Dr. Leela. Okay. And like I think we can start our talk, right? Is it audible? Okay. My screen is visible. Oh, now it is visible. Yeah, right. Okay. So we can start. Okay. And today we are going to discuss about this emerging trend in photovoltaic and optoelectronic application. And first of all, I like to intro myself. So as the intro, so I'm Dr. M. Rajalakshmi, Assistant Professor and working in Theoretical Physics Department. And my area of expertise in both theoretical as well as in practical. In mainly I'm working in thin film and soldiers method and different methods I'm working, even in high temperature, low temperatures working. Let me go into the subject. Okay. And today, what we are going to discuss about what is the problem and how to rectify the problem. And if you look at what is the emerging trends in photovoltaic, what is clean energy? What is clean energy? And what is the difference? Is there like what is this? Often we are using as a renewable energies as a green energy. Is it the same or is the different? Okay, we know what is a green energy, so which is not emitting green gases or other pollutant during the production is called as a green source or green energy. And if you look out, second, my net is getting low. Okay, okay. Now it is clear. Can you able to see my screen? Yeah, yeah. So we can divide the clean energy into two types. So one is the renewable energy and second one is the non-renewable energy. And this is all based on the natural source. So how we can define this renewable energy and non-renewable energy? So for example, if we take a nuclear energy, so we can see so how clean because it is not generating any emissions or pollutions. So like whatever, if it is non-renewable, means it is purely we can take example of uranium. Okay, so how we can do this is considered as a renewable energy. So if you come for the like a renewable energy, how this is coming, how we are using these things, so constantly we have to get energy. For example, the natural resources like a sun, wind, so this is all comes under this renewable energy. Okay, and this is the things. So what is the differentiation for the green energy, renewable energy and clean energy? So as a green energy, so it's completely this is from natural resources. Okay, so what we can take, so 5 element we can take, so we can go under this one. And renewable energy, this is some kind what we can see, so we can have a infinite amount of things. So that means we cannot get throughout the time. So the natural resource, whatever like uranium or something, so we cannot get long time. So there is a shortages of this element like silicon, whatever. We cannot what is this recover all the resource like from the natural resources. And for clean energy, so of course we know what is a clean. Even in day-to-day life, we are cleaning our homes, cleaning rooms, everything, and we are trying to get a clean air. So this all clean comes to the energy that is entirely different. Okay, a clean energy. So what are the source we are using? Like example, suppose we are using some kind of like a, material. What kind of material means? Example, we can take it as wood or something else. So if you take or if you want to take something, so that should not produce like as electricity. Take electricity. Sorry for the example of wood. Electricity. If we want to use electric, how we can use electron? So in day-to-day life, like if you want to use fan or if you want to use light, so something that is converted into energy, electrons or whatever that. So where the basic electron is getting, how we can get. So anyway, that we have to so product based on that one. It may induce like a pollute our atmosphere by releasing almost this carbon dioxide, methane, all these things. So this you have to avoid. Okay. Okay. So I can why we need clean energy? What is the necessary? Okay. Now we can see the current scenario in our earth. What is happening everywhere? We can see the war, and we can see some industry more like more number of like polluted, and we can see more vehicles. So this is all like producing more amount of air pollutions, like here the burning of coals, all those things. What happened when you're producing more number of like pollutions? It affect our global warming. Okay, so if global warming now scenario, what is happening? We know due to the global, so we have so many conference and workshops based on this global warming, how affecting this is our climate, everything, not even climate. Apart from that, we can see, and we are what is this addicted of this, what was before it was we have a good rainfall, now we can see shortages of these things will produce more demand for this vegetative, all those things. Okay, this is all we have to keep in mind. So this generation is okay for what are the future generations, so they won't get any pure air or pure water, whatever. Okay, so this is all one side, and we have to run for this advanced, like what is this technology wise, we have to look out how we have to rectify this problem to get the clean energy for our day-to-day life. So in futures, what we have to do, we have to produce without polluting our globe. We have to produce these good sources with clean energies. That's the things here we are going to discuss about. Okay. And here I have mentioned something about the methane and carbon dioxide, how these data are producing. This is all known. And what is educated, how we can rectify. So as I said, natural resources. Often we are using this as natural, how it is possible, and how much amount of energies we can. This is could be with efficiency. We don't have any idea how part this is in current scenario, how this is working. We want to know. Like we are saying that the sun, wind, waves, and water, this was going to produce as a natural base, and in solar devices or solar things, how it has to be achieved, we have to do. Okay, right. Okay. Now come to this one. This is almost we can see. So, what is the rising awareness about this cleaning energy, and what type of transition sources we have to use? Okay, so what is the use we can both benefit for the people as well as in the planet? And if you see 26th January, United Nations of General Assembly, they declared that International Day for Clean Energy in 28th January. This is good. Okay, and so, what is the use of these things? We have to go for the decarbonizing energy generation. That's the thing. We should not depend on the fossil fuels or the reliance. We have to go for the decarbonizing energy without polluting these things. The slide, we can see this picture almost how we have to move towards the clean energy. The conversion like a coal, nuclear, oil, and natural. These are the things what we are using now. This is the things. In futures, how we can improve by changing all these things. How far we can go for this green energy, renewable energy like hydropower we can use. Okay, and like wind, solar, biomass. Especially now we can see biomass is a major playing role. Okay, and biogas, in some villages they are using this geothermal and low impact hydropower. So like this we have a more things. Okay, we can go for this one, green power. So slowly we can convert from this conventional power to this green power to save our globe. Okay, and and my area is like okay, this slides we can see later. Come to this one. So as I said, we have a different kinds of energy. So first we can see what is the wind energy. Okay, so different types of energy. This is also one of the energy. So this is renewable energy, we can say how we can from energy from the naturals. So that means we can convert this kinetic energy of air into electrical energy by using this wind turbine. Okay, so where we can use, so we can use to for like a we can use for charging of this battery, or we can go for the offshore power plant, large scale wind farm, or we can go for this water pumping and irrigations like that. So we have so many things. And apart from that, this is also, this is a renewable energy system comes under this one. Okay, and hydropower, this is also we are using in India, especially in Tamil Nadu also we are using this hydropower. So hydropower is basically is this flow of water, from the flow of water, so we are converting. So the converting the kinetic energy and potential energy of flowing of this water into electrical energy. So how we can use? We have to use a turbine to rotate, and we have to generate the power. So I if you look at this applications, the large scale hydroelectric power plants, and we can use it for pump storage energy systems and rural electrification, small and micro hydropower system, industrials, and like that we can go for like numbers of application based on this hydropower. So what is the futures? So high power energy conversion we can go for up to 90%, but due to this climate change as well as this in this scenario we cannot in futures. I don't know how it is going to be like a 90%. So either we'll get like what is this it may be like a drowning, decreasing levels of from 90% to 60 or something else futures, and producing of a low green gas emission during this operation. This is also very good, and we can go energy of from organic matter, and as I said biomass. Okay, so we can go from this nature, how we can store, how we can use this for in in which energy things, source and scale of bioenergies. Okay, for example, if you want to convert this bioenergy, so from organic matter, so this agriculture things we have to do this. Even organic waste also we have to like as a collect the organic masses, and we have to go for this carbonizing all those things, and we have to go for some preparations of based on the salt gel method or different thin film matters. So for example, if you go for the groundnut shell, so we can use that things. We can go for the wastage of the sugar can wastage we can use. Similarly, paddy waste, everything we can convert into something, some masses of this one. Okay, we can use the storage applications. Okay. So solar energy. Solar energy is also we know what is if now often we can see in this like what is this in many of the small industries or in roadside we can see automatically we have a switch on and switch off light in the street. So that is based on the solar energy. So how the solar energy is working, this is purely based on the sun. So here this converting into electrical energy or thermal energy. This is something relevant to this photovoltaic we can see. So applications of solar panels we can see, but the development of solar cell is very complicated, but we can see the application is also very good. And for even for nowadays we can this solar energies we are utilizing in space and remote communication systems, and we can see like solar water heater in many applications, electrical generation, electrical vehicle charging stations, like that we can. So we can say like number of application based on this also solar panel. Okay, I'm come to this one. So now, so I'm fixing two my things. So we are going to discuss apart from the all green energy sources. So we specifically we are trying to work out and we want to find the problem in the solar cells, and this could be the next generations of the semiconductors innovations, and we can increase the cell efficiency and global scalability. So this could be the future of our things. Okay, and how to understand the semiconductors. Okay, so we know what is a semiconductor basically. So we know what are the different kinds of materials that's conductors, insulators, and semiconductors. Okay, and apart from that, so why we are specifically these semiconductors, and we are using these things means the major the band gap. Okay, so that means by increasing or by playing with concentration of token, we can go for many applications. Okay, so like charge carriers or electron charge carrier, so we can use and we can go for this enhancing these properties of the semiconductor. And if you look out, um, this photovoltaic, okay, and how it is going to be used for this clean electricity and zero emission. Okay, so we have to develop and we have to like what is this using the sunlight, we have to produce this efficiency, we have to increase these things, and we have to utilize this is a core. This is I think this you can see this is the principle how the construction, how the solar cell is working, and we can have just an idea about this material. Okay, and we can see this is almost as I said this semiconductors or photovoltaic this is relay, and we can see how they just like a PN junction. So how this is going to work. between in the mid ground between this electrical insulator, we can have it like a glass or metallic connector such as a copper. So why we are using these things to turn the energy from light to into electricity? We can see here the solar cell like absorbing this energy from this sun or some H nu, and we can see that sun exits electron the semiconductor material, so that conducting this electrode and produce electrical field in these things. Okay, if you want to get something basic about that one, how it is working, so we know what is n type and we know what is the p type, and how we can like what is this, we have read what is a p in junction diode, and that is producing this Shockley's effect. And we can here we can see this is a combinations of N and P type semiconductor. Okay, in between you can see this junction layer. So we know what is N type, we know what is a P type. N type means the majority is carrier is electron, and P type is majority carrier is holes. So now we can see this is, and I have connected to the external load, this electrical field. Okay, now what I'm going to, I'm going to shine this one. Okay, so when you shine this photon on this basis, so not on the entire surface, so this can be like what we can pick the pictorial space, depend upon, like for example, if you look pin diode, pi, like a pn diode means pin, pin diode. One second. Pin diode, we have seen what is a pin diode. So normal p-n junction layer will have like a p-n junction region, and in between you will have a small layer like in between, so we can have one more intrinsic layer. Okay, so apart from that intrinsic layer, if you shine a photon, what will happen? So the intrinsic region alone will absorb those things, these electron and positive sides, which on both the sides charges, that is recombinations will take place, and H2 will be created inside. Okay. If you want more efficiency, you have to increases the center part, the intrinsic region, by adding N plus or P plus different doping regions we can add. So by increasing the intrinsic region, so we can produce more number of charge carrier, and we can produce more amount of efficiency in that one. Okay, so this is the things, and now we can see this is a general constructions of your basic n type and p type, what we have discussed. So where we know what is a hole and what is a like an electron. So when you apply, what is happening? Okay, so how this, so when you shine a photon on the surfaces of the things, that means we will have some anti-reflecting coating on that one, that will absorb those light energy. Okay, when this absorb energy, what will happen? This energy, okay, so will induces, so the electron and that in the n type region and this p type regions we can see. So by increasing the electrical field, so we can see the electrons are started to flowing on that one. It's not electron always will be flowing to opposite to this electron, so we can see that recombinations will taking place only at the center of the regions. Okay, so now, okay, now what is the thing, what is the we have to focus, where we have to focus is not only the generations of this electrical field, we have to store, we have to store this energy, and we have to utilize the solar things, this thing we have to immediately, we have to use often, we should not like we don't have ability, such more ability like storing of information, this one. Okay, now come to the things. Okay, so three generations of solar cell. So first, like when you're discussing about the semiconductor, sure, one thing's come in your mind, the silicon and germanium. So that is a familiar single layer material we can see without any combinations, like we have a multi combinations, like triple combinations or double combinations or whatever. So we are very familiar with the silicon. So what is the problem in this one means, we cannot like run silicon throughout the things. Okay, so that means we are how the silicon ingot is getting ready means, so we have to collect this natural sand, so that we have to put in a, like what is a jacrosy technique or something, we have to go for this one, and we have to heat that one with a sufficient 1800 degrees Celsius or something, and we once heated that will get molded, and we have to take from the ingot as a silicon crystals without any defect. So that means how much of energy, how much of natural resources we have to use was that one. Okay, so once like so throughout all for all optical applications, if you're running for this silicon, and think about that one, what will the futures? Okay, so that means we shifted after this first generations. We have to running for this alternate sources of this silicon. That is second generations amorphous silicon and cadmium telluride. Like that, we have gone for this one. So apart from the third generations, also we have started now the DSs and organic PV, quantum dot, and perovskites. And especially now, like a futures is perovskites. So this is very cheap, and developing of these things is not too complicated. Like by using this high temperatures or things. Okay, we can use this one. Okay. So now, why, like, what is this? I'm specifically now I'm going into this perovskites. So later I will explain the structures. So now, why we are focusing on this one, why we have given priority for this perovskite materials means, so we can see what is the energy band gap. This energy gap is very important because that is 1.7. Almost we can see the range of things almost 1.2 something to 1.7 we can read. Okay, we can go, and we can divide into like three categories also. So different three categories, low, high, and middle. Like that, we can go for this one, or in low band gap, middle band gap, and high band gap. Like that, we can variations. So what is the attractive here? Why this is we are for specifically we are looking for this perovskite materials means because of these optoelectronic applications, various optoelectronic applications, like these are the things. Here I have summarized here some of the features. Like as I said, this is potential low cost fabrications, and by doping of iodine and chlorines, all those things, we can like what is this? We can tune the band gap energy. So according to the application wise, and it has a good absorption coefficient, and defect is also less. And what is the main thing? This is very lightweight compared to the silicons, and is so flexible for all applications. That's the main thing we are running. And where we are using, as I said, this is going to be next generations of photovoltaic. So we can use for blue LED or LED photo detector, and like that we can go for photovoltaics, WBG, and perovskites also we can use. Like tantalum is also in perovskites. We can go for this combinations of tandium. That is also very advanced one. Current scenario they are working on that one for increasing these electric applications, especially for increases at the voltage. So here I have explains about why what is this specific. We are not running for that one low or middle. So we are going for looking for this wide band of perovskites. Here I have given something like about what is this mixed halide perovskites and double and triple perovskites and chalcogenide and perovskites. Okay. Now you look, and as I said, we can dope this mixed halide perovskites like iodine, bromine, and like we can see. So why we are why by adding this dopant like this iodine or bromine, so we can change, we can play with this band gap that can vary, that can tune this 1.5 to 2.3 electron volt. Okay, and so for example, methyl PB, that is bromine. Like that, we can go for some inorganic and organic one perovskites and double triplet perovskites. So if you look at your double or triple perovskites, like example of this one. So why we are looking for this, because it will range is 2.0 to 2.3 electron volt, and here this is also, I said operating, we can based on this one, right? We can go for this operating application. And chalcogenide perovskites, we can see the lead free chalcogenide perovskites, such as the barium, zirconium, and X3 possess band gap in the ranges of 1.8 to 1.9 electron volt. Okay, so like that, so we have to go for these applications that should not like pollute our atmosphere or tropical things. We have to go for the non-toxic communication. That is our aim. So this is all friendly use. We can use this one. Okay, here I have the tablet. I have given some. What made this solar cells which stand out? Okay, so we can see here cadmium tellurium. Like example, have given us crystalline silicon and perovskite, and CHGS have given. So like that, we can see what is cost of this material. How, as I said, silicon I said. So we have to get in the bulk form, and we have to give more amount of energy. And if you look at the fabrications, we can slide out, and we have to move for the grid portions, and we have to go for the energy packaging. Everything is with now, and we have to main thing, we have to go for the efficiency. look out here, all this what is summarized here. So everything for rock cast, we can see this cadmium telluride is value and CHS is very medium, and perovskite is also coming under. So apart from this four material, we can see the perovskites are giving very good, and we have efficiencies very low. So cost wise and finishing material cost, application cost, in all way we can see the perovskite is suitable for our India, and we can go for these case. Okay, and silicon, as I said, silicon. So we have come across, and this could be the primary in like what is this 1950s. So without silicon, so we cannot do anything else. Now, even though we can add, we cannot fully negate the silicon. Okay, so we can go for the gallium and things. We can open the silicon, and we can improve the things efficiency with it. Okay, so what is the playing role? Now we can see for this perovskite, we can add this dopant and we can increase because of the sun ray spectrum. We are using this silicon, and we can see this one. Large silicon crystal, how this going for this multiple steps of manufacturings on how we are utilizing a lot of energies. So that is also creating this one of the important points for the clean of energy. And we can see, as I said, by doping all those things, we can tune the properties, the band gap of these things, as I said. Okay, and this perovskites such as low fabrications of low cost energies and compositional various things. By doping, we can go for this matching of this sun spectrum ideally. So that's the things we are looking something different from this perovskite, okay, from this silicon 2, and we are going for the third generations. So in what is the efficiency? So we want to see what is the efficiency when you're talking about those things. So everyone will look out. So how that efficiency will be? Even if it is low cost, we cannot say that could be a that will not produce the more efficiency. So that will be a possibles of efficiency. That's we can see here. This is 25.2. This record stand. Okay, and we now I think we can increase these things by doping all those things, a tandem or something else, we have increases from 29 to something else, we have increases. Okay, so soon it become a, like what is this will be in the increasing of more percentages, and we'll like what is this we're looking for more applications wise. So because that could be like what is this every normal people will be utilizing all those, and that should be everyone should be getting of these things, advantages of this device. That is the thing. So device, what is the purpose of device? So device should not be used something like a higher cadre. That should be rotated among this lower burners also. They should be utilizing those applications. That's our main things we're looking. What is the current research objective for this one? If you look, why we are looking at this research? So perovskite is increasing this silicon tandium. So we can use now. We have look at many companies worldwide. They have started and they have focusing on this one, how to improve the performance and the reliability and manufacturers of this based on this open of this perovskite. Not only the things, they are like opus conversions efficiency, like efficiency also from 27 to 20, like a 30 percentages. They have increases almost from 23 they have increased. Now almost we are in 26. Okay, so we can see achievement something is 30 when regions we are using most of the perovskites, and now researchers are looking for the new cell designs. So how to encapsulations, so how to charge us, all those things. I think I said now storing. So now we can EV vehicles is there, and we have a smart watches. In those things also we can use for perovskites. So that's the things we are tuning the students and tuning the resource scholars for developing all these perovskites. Okay, and that is shiftings. Where is it? Okay, okay. So now come to this perovskite structure. One second. Okay, so this is our perovskite structures. Okay, this is the simplest one we can see. We have A, B, and X. Okay, we can play with this. So what is A and what is B? A and B are cations, and X is anions. Okay, so by playing with this, and we can change the thing, and we can form a bond, and this giving a perovskite special structures. Okay, And most of the things, this is an example what I have given here: cadmium, uh, titanium, and trioxides. So they have used for this one because this is the most common example of this one. Okay, how we have to go for this? That is a number of methods is there, and what we are working on this one, we are working on this one like a salt gel method, and spin coating methods. We are working how to synthesize process by using this. Have demonstrated here. So as I said, this methyl ammonia, lead bromides. Okay, so we can use these preparations of this metal with the doping of iodine, that is, or a chlorine, or within phosphorus. We can do this one. So we can see how this is quite easy for this preparations of this gel, and we can go for this placing in this one spin coating. By employing that in this one, we can coat a thin film and we can use it for this one applications. So once here in this, we can see this is one step coating and this is a two step. We have divided into two steps. So first we have to prepare the material by using the solder process. Then we coated on that one. What we have like what is a spin coating method? We are spinning this one, and we got the coating on this one. Just we have to anneal. Okay. Second step, what we have to do, we have to go for this one. Either we have to go for like a rinsing methods or things, and we have to go for annealing these two things. Okay. When you go for this annealing, so we can see. So this is another method of coating this material. Like that, we have a two steps of this one. Okay. So this based on the salt gel oxide perovskite is where we can use. Okay, so the applications we can see here for this electric capacitor, solar cells, sensor, photocatalyst, thermoelectric, ferroelectric. So like that we can see the number of things. So we are focusing on the solar cells. So there is, as I said, depend upon the band gap. Okay, so we can go for the single, or we can go for the double one, or this. Okay. Okay. So working of perovskite solar cells. So what is in things we needed? Metal electrode, okay, we needed, and then hole transfers. What is a hole means? A hole means electron. We need a positive charges for this one, and the observer's layer. The metal, as I said, this is observer layer, metal, ammonium, lead. Okay, so we can change this cation ions in this one. Electron transport layers of atom dioxide and possible observers layers is this. Okay, now we can see. So this is the initial one, and how we can IT coding, and we have coded on this one, and we can see. So when this sun is shining on this material, the perovskite material, we can see how this reformation is taking place. For example, look at this one. This is a layer, the construction and cross view of this one, and you can see here this energy. When you increases the energy, what happened on this F2 material? So first we can see how this electron is like what is making a transition from one step to another step. From perovskite, this is moving for the FTOs, and we can see these holes are moving towards this thing. Like that, we can see things. Okay. So now this is C. Step is how we can go for this ABO3, that is double or single perovskite. Okay. So we can see. As I said, with this double and the single things, ABO3 is a combination for the single one, and for the double A2BBO6, right? Okay. So we can see how we can use this one precaution solution we have used, and we are converting into first we have to use this precautions. I use the metal salts and for this case, and gelatin agents I have used for the citric acid for this one. And the hydrolysis polycondensation is taking place, and then what we have to do, we have to form this gelatin. We have to leave for some hours, and we have to form the gelatins, and this will work how this gel like a polymeric network will be built. And we can see that in this gelatin region, the level of molecular is also like a good mixtures, and you'll have a uniform distributions of cations into the gelatin. And once gelatin is formed for the like a parenting solution was formed, and we have to substitute into the drying one for the solvent remover. And we will have a once we are like once we have go for the drying, so we'll have a good porous inside that one, and we'll have a shrinkages of the materials. So after the drying process, we have to go for the calcinations, like a 500 to 900 degrees Celsius. We have to go for the calcinations, and we'll have a good harmonic decomposition. So once the calcination is reached, we'll have a good crystallinity in that one. And finally, we'll obtain a oxide peroxide, and where we are using this electric properties, electric properties, and magnetic and hydraulics, we are using this one. Okay, this is summaries. And depend upon the temperatures, how we can go for example, here I have given the summations of the calcination temperatures and how the physical properties this application is used. For example, if we take a barium titanium trioxide, we can this nearly is goes for this 800 high dielectric constants and tetragonal distortions and multi-layer capacitors. And similarly for bismuth of for 3 or 6 and the ferroelectric behavior, electric and antiferroelectric we can go for, and this lanthanum and nitrogens or 3 we can go for this nearly 750 before go for this annealing or things metallic conductivity. So this is used for electrolyte and electrocatalysts and barium strontiums. So you can go for this nearly 800 that use good tunable electric field. Like that we can go for. So playing on this cation and anion, we can have a good like a devices. Okay. So what are the gender ones? Like what we have quoted, one we have confirmed that like what is this? Once we have quoted by using this sol gel method or a spin coating method. So we have to go for confirming our materials. So we have to go for the general characterization like XRD analysis and UV analysis, same, and electrochemical and photovoltaic performance. We have to see what is the efficiency of those things. So we are familiar with this general characterization, and here I have given some example. So how this is, we can see this pure one, that is methylamine and lead bromide, okay, iodine bromide. So by adding of aluminum 2% and 4%, we can see how this XRD pattern is shifted. Okay, so we can see. So while doping of this 4% of aluminum, we have a good like what is this growth in this 111 phases compared to 112. Compared to the pure one, we have enhanced the crystallinity of the materials. Also, we can see the X like what is this Y-axis. We can see the intensity is very sharp, and we have confirmed. And here this picture is giving something about the flame information, how the grain size, we have by doping, how we have increases the grain size is nanometer. So for pure material, we can see that is in black color. So we can see that is a grain size is almost like a 24 to 25 something this. But for the 2% when doping this aluminum, we have getting like a 32 to 34, like we have a good 33 something as we have got grain size of nanometer. For 4, it is it's not enhanced, but we can see this one. Okay, so 4% it is almost 29% nanometer size. Okay, now so as I said, by adding of this, we can tune. First, we have confirmed now. So whether the dopant have placed in the appropriate price and giving the crystallinity, and it shows a peak that is thicknesses are given. Okay, and next once confirmed, we have to go for this optoelectronic application. Especially, we have to see where the observations part is very important. That transmittance region is very important. By looking at the transmission regions, we have to choose what kind of applications we have to go for this optoelectronic. And here once again we have calculated what is a band gap one, and we have calculated what is a refractory index on this one. We can see for this dopant we are almost calculated for pure and 2% or 4%, and we can see this good improvement in this one. Okay, so by doping we can see enhancing of this one to almost 1.6 something we have to get for the perovskites. Okay, for red we can see this is almost nearly that 1.9 something as we have reached. And here we can see this is band gap regions. This like this is first we can see this is almost 2 point something is in this one, and this is below this 2.1 something we can get in. There is nearly 1.9 something is, and this is also 2 point something. You can have this is also good 2% is showing a good efficiency of this one, and refracting this also is calculated. This is also good in this how much of what photon was observed in this material. Okay, and so something, what is what is the advantages and disadvantages of using all those things we can discuss. So for perovskites, we can go for the high efficiency because of low cost fabrications is another one important, and lightweight accessories we cannot carry a heavy load or something else. So we can see this is and flexible is also because of this high coefficient. And what is the problem is one how to like what is this we are running back moisture. The moisture is one of the things we have to maintain the stability issues in this one, and we have to look for the thermal, another one, and light degradations. So because we are using this H nu, this photon, light degradations is very important. We have to look out for the light degradations, and what is the durability challenges we have to face is lifetime is very important, and toxicities is also when we adding for this lead or iodine something else we have to go for this environment pollutants also in this one, and environmental exposure risks risky also we have to look at for this one. Okay, and the things. Okay. Now, what is the utility of the scale of this clean energy development? Why we have to look in deep of this? Because of rapid expansions on decarbonization impact and decentralizations of this one. What do you mean by rapid expansions means? So global solar capacity continue to set what is the annual record they have to do that one, and the multi terahertz they have go for like a increasing the powers that should be like a cheapest one the new active. That is the aim. So that's the things they are running behind this rapid expansions of this one and decarbonization. If you look out, so we have to like produce without any pollutants or emissions. That's a goal. Okay. So without like we should not go back to the fossil fuel generations. We have to avoid this fossil fuel. So we have to look for this photovoltaic. So by choosing this different combinations of this one and decentralizations, resiliences, and we have to go for this microgrids and rooftops arrays. Like that, we can go for this in many industry lines. Advanced technology and materials. Why we have to push? As I said, we have to go for this one. So as I said, we can go for the silicon tandiums for this one perovskites. So for applications of conversions, 30% and bifacial modus. So what is the bifacial modus means? Capturing of direct sunlight from the on-print, and then we have to go for this. That should be observed with the material that has to produce a car charge carriers that will boost up the energy. Okay, and third one, so efficiency is okay, but what about this flexible material life? Okay, so if it is too heavy, we cannot carry on, we cannot go for this knocking corners of the world. So it should be like a, it should be lightweight and it should be a portable one. So we have to looking for this material portable, like a photovoltaic, and so we have to go for this new running of the material, like a engineer new in by using this different combinations in semiconductors. We have to develop what is the integrations of this and new architectures of this world. Okay, so even for the vehicles also you can replace this material. Not only for the domestic applications, we have to go for like a satellite applications also we have to do. That's the things we have to carry. If you want carry for this space station, that should be a very thing. So we cannot like a too heavy, we cannot do carry one. This is the laboratory innovations. So if you want to overcome the material constraints, what we have to do? Okay, so we have to do the research on this one, and we have to look at the chemical stability, and we have to focusing on how to enhance the efficiency of the perovskite sky, and how we can go for replacing of this like a gold or silvers or something which is expensive. We should not. So we know. So how we have to rectify, and we can see this advanced labs in this method. So here we can see how they are developing. This is MOCVD, something they have worked out. So we can see how they're developing these films. Okay, so like productions of this worldwide, they are doing these things. Okay, as I said, efficiency in last a few slides before we have seen the efficiency of 25 to 27, but you can see the efficiency, bro, like a breaks 34 efficiency by using this standium. Okay, and this is something what is this quite larger 30 to 33 let's say engineering multiple one of things architect, we have to say like that one day. Okay, because by without developing all these engineering things we cannot achieve this one. That means we have to go for fabrications. That fabrication developing such a kind of this 33 to 34 percentages of this photovoltaic, and successfully we have achieved this higher for per square meters. That's a great thing. And the solar technology comparisons, if you look out, okay, so we can see the cell technology. What should be the traditional monocrystalline silicons? What is that? They are comparing what is a monocrystalline silicon and bifacials of HJT and perovskite silicon tandium and cadmium telluride like that. So they have compared. So we are working on this one, as I said. So this is second generation, this is the first generation, and this is the third generation. So Liquid, and this is the first generation, we can see 31 to percentage, 23 percentage, and second generation we have like a 80 percentages of 30%, and we can see that third generation is giving almost 24 to 34 percentages efficiency. Okay, this is very good. And compare now come to the production cost. So we can see the production cost is almost like a moderate, and we can see this is also very low, but this is developing. as I said, we can see this is also perovskite. This is also low as we said, but we are like when we go for this architect, we have to go for developing of this combinations of different material, and we have to look out this one. So it is called developing one, and where we are using these applications. Okay, so in this monocrystalline silicon, we are using for the commercial residences proof, and for the cadmium telluride, we are going for the scale and thin film forms. And this bifacials, we are looking for utility scales and ground mounts. But for perovskites, we can see that this is the next high performance generation performance. And commercially model our efficiency evaluations of this one. So what is the percentage efficiency of this model of efficiency standard silicons in 2015? So we are almost back 10 years, almost we are cross. Okay. To 16 point. Now we are in almost 34 or 36 efficiency candle emergency tandem, and we can see 21% and 28% of this one. Now we are in the emerging trends of this tandem. We are almost at 36 percentages. Okay, so like that, we have to continuously run for the materials. We have to go for the combinations, and we have to look at what is the efficiency, or it is decreasing or increasing, whatever things, and we have to go for things for the integrations and futures of foreigners. So where we are using this floating PV, you can use an agri-voltage, you can use, and we can go for the smart grids and AI. We can use this one. Like we have so much of more AI and giving more information about what kind of metal we can use, and how it is going to be like a bonding with the A or cation or B anion. And what about this circular economic? All those informations is getting in this one. This is my future horizon for this one. Okay, so clean energy is not only the clean alternative, it is the most scalable of the cornerstones of a global zero net transition. The word zero, net zero transition is very important if you want to produce a clean energy. That is what we're looking out. Okay, and this is my future's challenging of the ferrous case solar cell by increasing the air and temperature stability. We can use this one. Okay, so like that, we can go for the finding of left free light absorbing material. And here I have summarized some applications. Here we can look out. This is something integrated photovoltaic conversions. As I said before, so not only we are developing the photovoltaic, okay, by using this solar cell. So we want to look out how to store the energy. So now what we are doing, we are coupling this lithium ion battery and superconductor with this perovskite solar cells, and we are storing the energy via this lithium ion battery and supercapacitors. Okay, and here we can see this is some of the model of this perovskites. So here we can see the perovskites of it's not clear, but we can see here that initially how we are making this electron transfers and hole transfers. And here we can see these combinations of how this cations is replacing, how they are forming with the electrolyte and a lithium ion battery, as I said now. So we can see in this slide, this A and B slides. And here I see this one, how the sunlight is falling on this in perovskite material. So how we can go for this emerging like a storing of information, so energy in this one, and how we can utilize to for this current domestic ones. And we can see this is two electrode capacity integrations. So once the electron is transferred, we can see this perovskite from this energy converting and we can storing all those things. This is single layer, this is a double layer. Like that, we can go for triple layer. So like that, we can go for the combinations of perovskites and we can work it out. Okay, and as I said, this is one kind of energy storing, and how to store is in vehicle. And in this slide, we can see this is showing how we can use a brace delay. So with the informations that giving information monitoring about our bodies, and that will give information based on this. Okay, so that is also used. Like that, we can use many applications. So what we have processed in day life. Okay, so finally, so I can try to conclude that one. So what we have seen, so how this perovskite, why that is important, and what we have to look out. We have to look out for the wide band gap of these perovskites, and how it can be used, how we can like what is this? We can make coating a thin film. What method we have to go for choosing, and how we have to do, and what are the material initial characterization we have to go for. These are things I have said. And what are the application, what is the final things once we devices like a fabricated is not like a, once we have coated, that's not a like a, that's not end of the work. So we have to go for some applications that application should become into the commercial one. So for the public use, that is our main goal. So we have to go for the photovoltaic, LED, and photodetectors. Okay. So what is a challenging in this one? We have to look at, as I said, stability, efficiency, fabrication, complexity, and especially in the carrier transport limitation is very, very important in this one. So only we have to change, or we have to play with the band gap, and we have to bring the efficiency. Okay. So by addressing all those things challenging, so I hope we can have a full potential wide gap, band gap perovskites in futures. So that will be like a with high efficiency, and it could be environment friendly also. So that we are looking for those energy futures. So these are the my reference, few reference I have mentioned here. Thank you. Chat box. Where's the chat box? Okay, I hope you have understood. Okay, so I said three different kind of like a wide band, like a band gap: normal, intermediate, and wide band gap. So we are looking what we have discussed about mostly this wide band gap that is greater than energy gap is 1.7 electron volt. So if you like what to say that one, if you want to go for like a normal one or intermediated, so that will produce an energy gap of lesser than 1.4. So that is not good for most of the optical applications. We have to go only for this 1.7 electron volt. One second, I'll search where my slide is there. Okay, okay, that means I have to close this one, right? It's closed now. You want to open my presentation or you want to close this presentation? Yeah, right.